Okay, so we're going to look at integrated rate law, which for us is 5.3 concentration changes over time. Integrated rate laws are going to show how the concentration of a reactant depends on the time. When we look at these reactions, we want to determine what their order is because we have different information given to us about the different orders. When we look at a first order reaction, this by definition is going to have the rate law of rate equals K times the concentration of A, or the change in concentration of A over the change in time, where we're going to be using up A concentration. Again, look at that negative sign. That's known as our differential rate law. As our reaction is going to proceed through an amount of time, we can monitor the progress of this with the integrated rate law. This integrated rate law for a first order reaction is given to you on your equation sheet for AP Chem as follows, which is the natural log of the concentration of A T, that is at whatever time we're looking at, minus the natural log of the concentration of A initially. That's going to be equal to the negative rate constant times time. Okay. The first order reaction, just like as we looked before, if the concentration of the reactant is doubled, the rate of the production of the products is also going to be doubled. We looked at this with the method of initial rates. One really important thing to know as we are looking at our problems is that radioactive decay for a nuclei is always going to be a first order reaction. You're going to see this in one of your problems in the practice where you're told about I think it's technetium 99, where you are just told that it's the decay, and we want to know that that is, again, first order. Okay, when we look at this, we want to look at this rate law as the relationship between concentration of time. What we can do with this is we can reorder our first order integrated rate law into a slope-intercept form. We're going to have y equals mx plus b, where y is going to be the natural log of concentration, the slope of our line is going to be our rate constant, and then our y-intercept is going to be that initial concentration. Okay, if you plot this data, it's going to give you a straight line graph. Okay, take a look. This one is natural log of pressure of CH3NC versus time, and you can see that the natural log is going to give you a straight line graph. So that means it's going to be first order. Okay. All right, let's take a look at an example here. How long does one have to wait for the reactant in a first order reaction to decrease by half? Okay, so if we use our equation as we're given here, we want to look at when our concentration is cut in half. So that's going to be half of our initial concentration. We can plug this in. That's going to be our new concentration. Okay, this is going to be half of our initial minus the initial, and that's going to equal negative KT. Okay. We plug this in. We're going to solve for 1/2 of A over A, take the natural log of that. That's going to be equal to the natural log of 1/2. Okay, and that's going to be equal to negative K times T. So that's going to give us negative 0.693 equals negative K times T. On your equation sheet, we're going to get this half-life equation of T1/2 equals 0.693 over K. Again, this is going to be for first order reactions. The good news is that you don't have to derive this again. This is going to be given to you when you need to calculate that half-life of a first order reaction. A half-life is just the amount of time it takes for the original concentration to be cut in half. We can look at these successive half-lives as we go from 0 to 100 seconds. We cut from 0.1 to 0.05. Then we go through another half-life of 100 seconds. We cut that in half again. Okay, and then a third half-life, we would cut that remaining sample in half by 1. So we can see here for this that this is going to be a half-life of 100 seconds for this particular sample. Okay. A graph for a half-life of a first order reaction, again, it's going to be the amount of time it takes for each half-life. This is going to be its constant for each half-life as we're looking at that. Okay, here's an example where we can see this at the particulate level. Okay, this is concentration of A versus time. This is going to be any unit of time, but we can see at T0, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 particles. Okay, after one half-life, we should be cut down to 8, 2, 3, 4, 5, 6, 7, 8, then down to 4 after 2 half-lives, and finally down to 2 after 3 half-lives. Okay. All right, that's first order reactions. Again, natural log of concentration versus time is going to give you a straight line graph, and then radioactive decay is always going to be first order. Okay. If we're looking at our second order reactions, I'm going to change colors here. Second order reactions, we're going to have rate equals K times the concentration of A squared. Here we're going to see, just like we did with method of initial rates, that if we double our reactant concentration, this is going to quadruple our rate. Okay, again, we can monitor this in a similar way using an integrated rate law for second, but this time we're going to see that it is the inverse of the concentration versus time that's going to give us a straight line graph. So our slope-intercept form for this is going to be 1 over concentration of A at our time is going to be equal to positive KT plus 1 over the concentration of time. A big thing to notice here is that the slope is going to be positive for this straight line graph, whereas in the first order, it's going to be negative. Okay. All right. You can see here how we can derive the half-life for the second order reaction, where T1/2 is going to be 1 over K times the concentration of A. This is not going to be something that you're going to be asked to do using this equation, because this is not on your equation sheet. If you were asked to find the half-life of a second order, you could plug in your information and you could solve it from there without needing that half-life equation. Okay, again, we're going to see that this amount of time doubles with each successive half-life. So this one is not going to be constant. Okay, here we can see from time 1 of 0 to 0.2, okay, of 1 second, we can see that we've got our half-life there. Now as we go from one time unit, let's say it's seconds, okay, now we've got 2 half-lives that have passed. Our second half-life is now going to be 2 seconds. Okay, now we're going to go to our third half-life, okay, and we're going to go from 2 up to 4 seconds. Okay, so we can see that second order process. Okay. All right. So this is a comparison of natural log of concentration versus time and inverse of concentration versus time. Again, we got that nice straight line graph. We've got a positive slope, which is going to be equal to our rate constant. This is going to signify that we have a second order reaction. Okay. When we look at the half-lives and we can compare those, our first versus our second order, okay, at first order half-life, let's see if I can get my colors to match what I had before. Okay, half-life is independent of initial concentration. It remains constant. Okay, we get that 0.693 over K, so it's dependent on our rate constant. The second order half-life, though, is going to be dependent on the initial concentration. Okay. Again, that's like what we just saw here. It's going to depend on that initial concentration, and it's going to double with each successive half-life. Okay. First order reaction, each successive half-life is the same, whereas our second order half-life, like I just said, is going to double each time. Okay, so if it's 1 second, it would then double to 2 on the next, to 4, and so on and so forth. Now, lastly, we want to look at zero order reactions. And this is going to be a situation where we do not have an effect when we change the concentration. Integrated rate law for a zero order reaction is just going to be the concentration at our time minus our initial concentration is equal to negative KT. This is what we have on our equation sheet. Rearranged in the slope-intercept form, y equals mx plus b. Big thing to get from this is that the slope of the line of your graph is going to give you the value for your rate constant. Your slope will be negative, so you will want to take the positive value of that for your rate constant. Okay, slope is negative k, and your y-intercept is that initial concentration. Okay. With the zero order reaction, the reaction rate is independent of concentration of reactants. So it doesn't really matter if the concentration of the reactant doubles, the rate just remains unchanged. A good example of this is the metabolism of alcohol is a zero order reaction. If the alcohol is consumed, the increase of the amount is not going to change how quickly the body metabolizes that. It's going to metabolize the ethanol at a constant rate. There are a lot of biochemical reactions that are zero order, and that just means that the concentration isn't going to change the rate. These really will depend on the catalyst. You could, again, use the half-life equation that's given here. Don't feel like you need to memorize this. We could use a half-life calculation in order to find this as well, but half-life for zero order is going to be the concentration of A divided by 2K. We'll switch gears here and take a look at a few examples from the practice problems.